This is a Google image search for motion. I'm going to read an excerpt from an introductory physics book written by Alonso and Finn. The most fundamental and obvious phenomenon we observe around us is motion. Blowing air, waves in the ocean, flying birds, running animals, falling leaves, all these are examples of motion. Practically all imaginable processes can be traced back to the motion of bodies. One role of physicists and engineers is to discover the relation between motions and the interactions responsible for them and to arrange things so that useful motions are produced. This excerpt was meant as a motivation for these chapters on kinematics, where in an introductory physics book we throw these variables and equations at students that cover time, distance, speeds, and acceleration, and so that students hopefully get an appreciation for, well, we have to do that because motion is so fundamental that we're starting out with that before we do anything else. The drawback, of course, is that we have these equations that at first look very strange, and then we make students calculate quite a bit of problems with these here. However, we still try to apply them to everyday motion and make lots of examples with these. One objective that I have in this recording is to show that these equations don't come out of the blue. They kind of look strange, but there's meaning behind them. And so in this Word document I summarize that. This one here, what I call the first equation, the final velocity equals initial velocity or speed plus acceleration times time, simply is you're going down the highway and you're driving 35 miles an hour, and then you accelerate for 5 seconds at a certain acceleration, 4 miles per second per hour, 4 miles per hour per second, and so you come up with a final speed of 35 plus 4 times 5 equals 55 miles an hour. Again, it's a very familiar scenario. You're driving at 35 miles an hour, you accelerate for a certain amount of time, and you come up with a final speed, and that's all this equation here actually means. And then of course you can algebraically turn it around as well. Little side note here, we are actually not familiar with accelerations in our everyday life, especially when it comes to driving a car, mainly because the units are so strange. Notice this one here, miles per hour per second, and it doesn't get any better if we switch this to kilometers per hour per second. So that is perhaps why we actually never attach a number to acceleration. Okay, so that's the first equation. The second equation is actually all just distance equals average velocity times time. That's really what it says. So you're going 55 miles an hour and then you accelerate over a certain amount of time to 65 miles an hour. Your average speed, of course, during that time interval is 60 miles an hour, and then you're going to drive that for a certain amount of time, that average velocity, and you come up with a certain distance here. Now, the reason why this looks so complicated with the 1/2 Vox plus Vfx is that when we take the average of 55 and 65, we have to express it mathematically, and while in our heads we just say 55 and 65, well, the average is 60, when we actually write it down, we have virtually no choice. We have to write it as 1/2 of 55 plus 65. Notice that there's really no other mathematical way to say that the average of 55 and 65. So we have to write as such, add it, take 1/2. That's really the only reason why this one looks so complicated. So far, the first two equations that I point out here are really ones that we're familiar with. And this one here, The next equation then, we're also familiar with the first part. It's simply distance equals speed times time, but then an acceleration is going on for a certain amount of time. Notice that this equation here kind of covers the same thing as this one here, except that there's an acceleration written here, while here there is actually a final velocity written. And you can see that the two are actually equivalent with each other, because one of them had the final velocity substituted out of it by the use of the first equation. That's just out of the picture by using this one here, and therefore the algebra then yields this part here at the very end. As an example, this would be, for example, you would be approaching a school zone. You're driving a normal 35 miles per hour, and then of course you're supposed to slow down to 20 miles an hour. So for 5 seconds you have a deceleration of -3 miles per hour per second. Very weird units. That's why I converted these here to a -4.4 feet per second, and I also converted the speed to 51 feet per second. And so going from 35 minus 3 times 5, that would be -15, so 35 minus 15 reduces the speed to the required 20 miles per hour in the school zone. And so the entire equation would be that the distance equals all of this one here, and the outcome is that you have about 200 feet prior to the school zone in order to slow down to the required speed. So again, this particular equation here, this one here is just normal, that distance equals speed times time, and this one here is new, and it comes from the algebra by using this equation here and this equation. The last equation is totally new and totally unfamiliar to most people, and the way it is derived is take the first and the second equation again, but at this point you divide or substitute out the time t, and then what you get is right here a difference of squares as you do that substitution, and here it is. And when you're done, you get this one here. This equation is used when time is not given, so that's why we need it. The equation is also relatively important because it will show up in the energy chapter again, where this one here, I think you can see the similarity of this one to this one here, where kinetic energy equals the initial kinetic energy plus potential energy. Notice that the 2, of course, over here became a 1/2 over here by dividing by it. Okay, this one here, you can read through my example yourself, that an expert in an accident investigation is measuring the skid marks and comes up with a certain initial speed of the vehicle according to those skid marks. When I was writing this here, the first couple of pages, I noticed that in a previous document I had already written that down, so I figured instead of just throwing it away, I just double up on it, so you can look at this one here and compare with the above. Of course it's the same, and look at either derivation.